Hello, my name is Isaac Hayward, and this is my Lab 2 Lines of Charge. The fundamental principles and models that we're using in this lab are Coulomb's law, represented by F equals 1 over 4 pi epsilon 0 times the charges divided by r squared, Newton's second law, which is F equals ma, and the superposition of E field vectors. And as you notice, we'll use both Coulomb's law and Newton's law to calculate for charge Q. The assumptions that we are bringing into this lab are that each piece of tape had the same amount of charge, charges on each tape were evenly distributed throughout the entire length of those tapes, and that we ignore air resistance on the moving tape. Let's revisit some important information from Lab 1. In Lab 1, we used a system of two tapes, a base tape and a U-tape, shown to the diagram on the right. Using this system, we created charge tapes, and we wanted to determine the charge of those tapes. To determine the charge of those tapes, we used two different U-tapes, and we saw how much they repelled each other, shown in the diagram on the bottom left. Using this point charge type model, we found that the tape rose up in 0.045 meters, and we determined the tapes have a magnitude of 2.1 times 10 to the negative 8 coulombs. The data we will use in this lab is as follows. The tape will have a length of 0.2 meters, a width of 0.02 meters, and a weight of 0.0002 kgs. And the charge of the tape from Lab 1 that we'll be using is 2.1 times 10 to the negative 8 coulombs. Here's a quick rundown of my glow script code. Over here are my variables, the constant K and the gravity constant. And down here is how I calculated my electric field using the formula electric field equals K times Q over R squared. Since we are no longer looking at a single point charge and now we're looking at multiple point charges, these lines of codes will help us produce a line charge of multiple. The bottom two lines of code will help us determine how many arrows we want to see to represent our line charge. And in this case, I chose 100 arrows each. In these lines of code, we are calculating the electric force on the top tape due to the bottom tape. By using superposition, we are adding up all the bottom tape and the charges of those bottom tapes as they interact with the top tape. It is important to note that in this code, we are ignoring any interaction with bottom tapes with another bottom tape. We're only focusing on bottom tapes and their effects on the top tape. With these lines of code, we are simply just creating an arrow to represent the electric force vector, the gravitational force vector, and we are simply printing out the answers we calculated with the code above. To help you better understand our computational model, we could calculate for the charge of tape ourselves. Since we are dealing with a line charge, we are no longer dealing with a point charge, so we won't be using this formula, which is the electric field of a point charge. We will be using, however, the electric field formula for a rod. By utilizing both Newton's laws, F equals mg, and Coulomb's law, we can set these two equations equal each other and rearrange the equation for Q, which we found to be 3.5156 times 10 to the negative 8 coulombs. Let's compare our findings from Lab 1 versus Lab 2. In the diagram to the left, I inputted the charge of a point charge which we found in Lab 1. As you can see, the electric force vector is much greater than the gravitational force vector, which shows the inaccuracies of just using a single point charge. On the right, or this lab, I inputted the charge Q, which we calculated on the last slide. And as you can see, the magnitude of the electric force and the gravitational force are much closer to each other, showing that this is a much more accurate estimate. Possible sources of error can stem from the accidental discharge of electrons while handling U-tapes from the first lab, or human errors documenting measurements from the first lab. Errors from this lab could be based off of our assumptions that we made. The charges may not have been equally distributed, and the charges on the two different pieces of tape may have been different. Now, what if we had modeled our tapes as a single point charge? Well, if we did, we would have calculated a charge of 2.1 times 10 to the negative 8 coulombs. However, we modeled it as our line charge, and we calculated a charge of 3.5156 times 10 to the negative 8 coulombs. When compared to the point charge value, the value of the line charge was nearly double, increasing by 167%. Why do these estimates differ, and which value is more likely to be closer to the real value? The value of Q that we calculate for the line charge model differed from the point charge value because we considered multiple charges instead of a single point charge. And I believe that the value of Q for the line charge model is more likely to be closer to the real value, as the model took into consideration for the distribution of charges along the entire tape, unlike how the point charge model only calculated for a single point.